Okay, so let's put some numbers to the previous question. We have a boat whose speed in still water would be 20 kilometers per hour, and the current has a speed of 12 kilometers per hour. However, we know that if the boat is going with the stream, it's going to go faster. If it's going against the stream, it's going to go slower. But if it's going at some angle, it's not going to just simply be added together. We have to use our vector addition. So let's first draw that river. Here's the river. Visualization and picture is so important in physics. Our start, and I will say the stream is traveling in that direction. So this is our water. So here's my first vector. And like what we saw in the previous one is that the addition of such that the water will push it back on course. So now we can think of it as the boat is actually going to face this direction, but it's going to move in that direction. So let's add some numbers to this problem. So we have 20 kilometers per hour, and the stream is 12 kilometers per hour. And as we can actually see right now, this is a right angle triangle, so it's not too challenging of a question. So we see that what must this angle be? We see that we have the opposite and we have the hypotenuse. So we have sine theta is equal to 12 kilometers per hour over 20 kilometers per hour. So we get theta is just equal to the inverse tan of those numbers. We end up with 37 degrees. Right. We can add a little bit more to this question. The question might be, what is the time to cross the width of the river if the river was 5 kilometers across? Let's add that one in right now. So what is the time required to cross this river given that its width is 5.0 kilometers? We can start bringing in basic kinematics that we saw last year in grade 11. So you say, okay, d is equal to vt, time is equal to d over v. But this is where it gets, we have to make sure our I guess distance triangle or displacement triangle matches our velocity triangle. So we actually have two triangles that are proportional to each other. So here's our first triangle, and here's our second one. So what we need to recognize is that like one of our triangles shows distances and displacements, while the other one shows our velocities. So we have 20 kilometers per hour right here, and we have 12 kilometers per hour. And we are given that the river's width is 5.0 kilometers. So 5.0 kilometers. So what we need to recognize is if we want to find that time, we need to get the matching vector. So if I want to be able to solve for time, I need to find out what is this velocity that corresponds to this distance or displacement. Alternatively, I can also use the 20 kilometers per hour along with this distance right here. Or I can use this 12 kilometers per hour with this distance, the river one. So if I use a little bit of trigonometry, we have 12, 20, so 20 squared minus 12 squared. And if I square root that number, so we get 256, square root, we end up with 16 kilometers per hour. So what we can see is that although the boat is traveling at 20 kilometers per hour, because it has to go slightly against the current, like if it was going directly against the current, we had 20 kilometers per hour, and it's going directly against the current, 12 kilometers per hour, it would only travel at a speed of 8 kilometers per hour against the current. However, it's not going directly across, it's going at some angle. So we can see it's going 20 kilometers per hour at that angle. The water is at 12 kilometers per hour. It appears to be crossing the river at a rate of 16 kilometers per hour. So we can write down 5.0 kilometers divided by 16 kilometers per hour. And we get a time of 0.31 hours.